This lesson looks at reflection, and this is part of the waves topic. We would normally start with a practical using a ray box as shown on the bottom right of this slide. We get a sheet of A4 paper, we place a mirror on the sheet and we draw a line along the mirror. We call this the mirror line. We then use a protractor to draw a line at 90 degrees to this mirror line, and it's called the normal. In maths, the word normal means at 90 degrees. So when we talk about the normal line in optics, we mean the line at 90 degrees to, in this case, the mirror. In optics, it's really important to remember that all angles are measured from this normal line. They're never measured from the mirror. We then draw a line at 30 degrees to the normal. 30 degrees an example, we could choose any angle. We replace the mirror and shine the ray of light along it using the ray box as seen on the right. We then measure the angle between the normal and the reflected ray and compare the angle of incidence, the incoming ray, against the angle of reflection. Now, I'd really recommend having a look at the YouTube clip shown on the video here, because it shows in detail how to carry out this practical. This diagram shows the results of that experiment. So on the right hand side, the black line with the lines across it, there's the mirror line. The dotted line at 90 degrees to the mirror line is called the normal line. The red incident ray is the one we shine into the mirror, and the green reflected ray is the ray that we see coming out of the mirror. And then we would measure the angle of incidence and we measure the angle of reflection, and we find that the two are equal. This is known as the law of reflection. The previous diagram was known as a ray diagram because it shows the path of a single ray of light travelling to and from the mirror. You may also need to know about wavefront diagrams. Now, this is more likely to turn up on the higher tier paper, but they have been known to turn up on the foundation paper as well. A wavefront diagram shows the peaks of the waves. So it's as though you're up above the wave looking down and seeing the peaks of the wave as they pass you by. So if you imagine that you're flying over the sea in a helicopter and you can see the peaks of the waves travelling towards the shore, that's what a wavefront diagram is trying to show. So when we have a wavefront diagram, it looks a bit like the one here. If you're asked to construct a wavefront diagram yourself, I would always start with the ray diagram and add the wavefronts on afterwards. The wavefronts are always at right angles to the rays, so you can draw them in once you've got the rays in the right place. And as you'll see, we always make sure that they are the same width, and in this case they're the same distance apart before and after reflection, because the wavelength wouldn't change on reflection. The second reflection practical is a required practical for the physics paper only. And you would normally do the practical whether we're looking at combined science or triple science. You're required to shine a ray of light from your ray box onto a piece of flat aluminium foil and then onto a piece of crumpled aluminium foil. Or in fact, we could use any shiny surface. And what we're looking for here is the difference between the two results. What we get when we shine the ray of light onto a flat surface is the diagram on the left, which we call specular reflection. And that happens because all of the light hits the mirror at the same angle and is therefore reflected at the same angle. You shine a single ray of light on the mirror and a single ray of light returns. If I shine a ray of light onto something which is uneven, I get something called diffuse reflection, which is the diagram on the right. You're still getting the law of reflection here. The angle of incidence still equals the angle of reflection, but because the light is hitting the surface at all different angles, it's also reflected at different angles. And the question is, why would we want to know this and where can it be used? Diffuse reflection is useful on any surface where you really want to be able to see it, where you want to reflect the light in several directions. So what we have with something like, for example, the road signs or the bicycle reflectors or the reflective coat is if it has a flat surface, then any ray of light shining on it, say from a car light or from a torch, would reflect off but only in one direction. You'd only see the reflected light if you happen to be standing in the right place. By using an uneven surface, diffuse reflection ensures that light is reflected into lots of different directions, which means you're much more likely to see the item that's reflecting the light, so the coat, the bike reflectors, or the road signs.